Good Thursday afternoon, everyone. Welcome to lecture 13 and maths for construction. What we did lecture 12, we talk about what a logarithm is. A logarithm is a synonym for power or index, but the context we use a logarithm in is when we have equations where the unknown is a power. So you see here, like 2 to the x is 8. What is x? X, the unknown, is a power, is not a base. So logarithms were invented to change this equation from an exponential form to the logarithmic form, where the unknown is a power, right? Your calculators just help you with these things these days, but I don't know what to type in, right? When you see something like this, find log 7 or 1 over 49, what they're asking you is for a power, and they need to give it the base. So what power must 7 be raised to give 1 over 49? The answer is -2. We have some laws of logarithms here. And then, we get bored with that because logarithms boring. And we move to integration. Integration is the process of finding the original function given the gradient function. It's the reverse of differentiation. In differentiation, we're given a function and we need to find the gradient function. And if integration is the reverse, we have the gradient function, but we want to know what's the original function that gave that gradient function. Integration is way harder than differentiation. Okay, it is way harder to figure out what function gave this gradient function. Generally, if I give you a gradient function, it's not easy to figure out what the original function was. But it's very easy to differentiate. You can differentiate almost anything, right? Have rules for almost any function, and you have your product rule, your quotient rule, your composition rule. If you have every function looks a little bit evil, right? If it's defined parametrically, if it's defined implicitly, we have all these techniques for differentiation, right? Which you don't need to know. But generally, it's a lot easier to differentiate something. But integrating, oh boy, no. Many functions, I don't know how to integrate. I don't know what the original function is. I have no way to figure that out, right? I gave you all this homework here. I expect you all to be able to do questions. This is a very easy question, huh? This example 7, extremely easy question. If you're having trouble doing this, then, may the force be with you, right? We want to move on to applications of integration. So we go back to our textbook. Well, our textbook, having it, boy. Areas under between curves, right? It turns out the area between a curve and the x-axis is solved by integrating, okay? They have some argument here to convince you that that is the case, right? This is more for your understanding, right? This is just to show you a strip of width delta x. The height could be interpreted as f of x multiplied by delta x is the area. So if the height is delta, sorry, if the height is y and the width is delta x, the area is also almost equal to y by delta x if you think of it as a small rectangle, right? A very narrow rectangle. If you add up all the areas, you're doing a summation, and that's what integration is. Integration is a summation process. But is the summation of a bunch of numbers as the limit, the difference between the numbers tends to 0, as the width of the strip tends to 0, okay? Limiting processes are very complicated. It took human beings several hundred years to understand the idea of a limit properly. So if you don't understand it in a couple of weeks, months, or years, don't feel too bad. Humanity took 900 years or so to understand it properly, right? Calculus was invented as a toolbox where people were doing things like this, people were doing things like this here, and they really didn't know how it worked. They didn't really understand the backbone of it, and the backbone of it is real analysis, all right? Which you don't ever learn if you're an engineering student. As somebody like me who did a maths degree, we had to be subjected to at least 1 or 2 courses of real analysis. One of the hardest courses you were doing your undergrad maths degree, right? But that is the theory that underpins the real number system and metric spaces, which defines the measure, area, and length, which in turn defines integration, right? So for many years, human beings use the results of integration. Like they did a question like this 500 years ago. They would do things like this, but they didn't really know how the hell it worked, right? It's long after that people came and really understood what the idea of a limit was. It's a very, very complicated thing. It sounds simple, but defeated mathematicians for many years, right? So the area under a curve is a definite integral. So we talk about that. What is a indefinite integral and a definite integral? This is an example of an indefinite integral where you're given a function and you find a gradient function. That's basically what an indefinite integral is. A definite integral has limits. And what you do is you apply the limits of the original function after you integrate to get a number, okay? So you see here, you have some formulas in blue here. The area under the curve between A and B, x equal A and x equal B, is the definite integral of f of x dx between A and B. So let me give you an example here. If you had this here, this question here, and this is an indefinite integral, okay? Let me give you an easier question here. Indefinite integral. Oh. So indefinite integral given a gradient function, find the original function. Essentially, that's what indefinite integral is, right? Let's do an example. So if I want to know, hold on. So if I wanted to know what this is here, you apply the rules of integration, right? This 3x squared here, you add 1 to 2, you get 3 and you divide by 3. So this is x cubed minus x squared plus c. C is the constant of integration. So we always have it here, right? C some number, 2, 4, 0, -1. We don't know what it is, right? So we write it in. Example 1. Definite integral. Given a gradient function as well as x coordinates. Coordinates means two things. Ordinate means 1. So we say with the x ordinate. Find the original function and substitute the ordinates into the function. and then subtract these values. Okay, so here, if I ask you integral between 1 and 3, okay, this is a definite integral now. This is a definite integral. And what's happening here is you're usually given limits. The lower limit is the number below, and the upper limit is the number above. These numbers don't necessarily be in such a way where the one below is always less than the one above, okay? There's no restriction on what the numbers could be. The number above could be more than the number below, it could be equal to it could be less than, okay? They don't really have a meaning there. But it turns out the evaluation of a definite integral is the area under a curve, which we'll see just now. So how you'll do a question like this? Well, you find the original question here. Let's see if this is work for you. Oops. I think you could do this. Right, this looks better. So usually we represent it as square brackets with the limits true to. What this notation here means is the value of the function when x is 3 minus the value of the function when x is 2. So like we could write this again. Minus okay then. So you do a subtraction and you put the upper limit on the left hand and you minus from the lower limit. So here with this would be 3. This would be 3. And the lower limit is 1. So 1, 1. Right? So that's what this is here. You integrate as normal, you get the original function and you apply the limits 3 and 2. I don't know why I have 2 there. It's supposed to be 3 and 1. Okay. So the upper limit is 3, the lower limit is 1. So you substitute the upper limit into the function and you subtract that from the substitution, the lower limit in the function. What you would notice is that the constant always cancels out. So you don't even need to worry about it when you're dealing with a definite integral, right? So you could omit the constant here because it's gonna go away, right? Eventually. What do I have here now? I have that's in brackets okay then. I'll have 27 minus 9 in one bracket. And I'll have 1 minus 1. 1 minus 1 in another bracket. 27 minus 9 is what? 18. 1 minus 1 is 0. So this is just 18, right? And we always say units. Unit squared. We could take out the brackets because it's a number. The answer is a number. Right? So we'll do that for A. We'll just say 80. The value of a definite integral is a number. Okay, it's not a function. At least not for the functions we deal with, right? So this is what a definite integral is. You're given limits, a lower and upper limit. You integrate, you find a function, you can leave out C if you want, and then substitute the upper limit and subtract that from the substitution the lower limit. That's essentially what the syntax here is, integral between E and the R f of x. It turns out as the area, okay? So we have graphs and curves where, and this is very geometric now, it's very spatial. The idea, your spatial reasoning how to be good in calculus because most of the problems involve pictorial graphs and curves in space, okay? So the area of a straight line very easy, you don't even need calculus for this. This is area of a trapezium, which everybody knows from primary school, right? If they give here a velocity of a particle, find how far it moves. And that's because integration gives you the distance. Area under a velocity time graph is distance. And you know this, right? You have a velocity time curve, the area underneath the curve is distance. That's why integration tells you what the area is. Here they ask you to sketch a graph and determine area enclosed by the curve on the x-axis. You can't do this question unless you know how to solve polynomial equations, right? So this is this is a tricky thing to do. You see here, if you look at the integral they're doing, the integral of this thing from -3 to -1. They integrate the original function, right? Look at here. They integrate the elements and they put the limits -1 and -3, just like -1 up here, -3 here. And then this thing up here, you substitute -1 and you subtract that from -3 being substituted. And you just get a number. So integration in this sense is actually not so bad because you get to substitute numbers into a function and everybody knows how to do that. This is not hard, okay? We will talk about trapezium. We'll find the area enclosed by the curve, the x-axis, and the ordinate x equals 0 and x equals pi and 3. Pi and 3 is actually 60 degrees. Pi radians is 180 degrees. Right? This is an angular measurement called radians. Right? Pi radians is 180 degrees. So you see the curve here, y equals sine 2x. Pi and 3 is this coordinate here, the one that shaded area, right? You have to integrate this curve sine 2x between 0 and pi and 2. So we integrate it here, see, integral of y dx. This definite integral here is the area under the curve. So, just to integrate it, apply the limits, you have two things to subtract. When you simplify it, you get 3/4. So that's really all there is to it, okay? But when they give you problems, that's when you have to figure out, you have to solve equations and so on to figure out where things intersect or where you cut the x-axis, where you cut the y-axis, that kind. Depends on what they ask you, okay? But it really is this simple. It's really an integral and you just apply the limits. So what makes the question hard is finding the integral. If you can't find the integral, you can't do the question. If you don't know how to integrate this function to get the original function, if you can't go from the gradient function to the original function, then you can actually do the question, okay? So we'll do some examples with this. How about the applications besides area, where area is the most popular use of integration, finding the area between a curve and a next curve, or between a curve and an axis, or pair axes, or something like that. That's the most popular use of integration. So we have this example here, and remember I told you calculus, both in integration and differentiation. Calculus is one of those topics where it is very easy to give you a question in a short number of words, and it is a very, very hard question. Okay, that's what makes this topic in maths very formidable. Right, it's highly feared among students. Right, it's very easy to give you a calculus question that fit in one line, and it might take you 3, 4, 7, 8 pages of working to figure out the answer. Okay, so just bear that in mind. Right, finding area enclosed by the curve. They give you the curve, the equation of the curve, on both the x and y axes. That's it. That's all they want. Find the area enclosed by the curve. Okay, so the area is enclosed by a curve on 2 axes. Okay, the x and y axes. So we kind of need to know how this curve looks like. Right? So what we should do is find out where it cuts each axis, just to get an idea. And really, you have to sketch a curve. That's how these things work. So so solution 3. You need to sketch a curve. It's a quadratic. With the coefficient normal quadratics are shaped like a U. So this shape like an upside down U, okay? Or upside down V. So we know it's shaped like upside down U. Where does it cut the x-axis? So here is our equation y equals 0, right? So let's do that. So y equals 0. What is y? Y is all this, right? So all of this equals to 0. So that's how this equation equals 0. So when this equation is simply multiplying everything by -1. So you get x squared plus 3x minus 4 equals 0. Multiply everything by -1 to make it look a little bit easier, right? This could factorize to test that out. You multiply the coefficient x squared by the C, the constant term. So 1 by -4 is -4. And what factors are -4 add up to 3? So the factors had to have different signs, like 2 and 2, +4, +2 -2, +1 -4, +4 -1, right? And they had to add up to 3. So we could use +4 and -1. So we write 3x as +4x minus 1x. Okay. And then you do a lot of partial factorizing here. Is x into x plus 4. Immediately when you find that out, you put x plus 4. And then you try to figure out what you need by the question mark, so that when you multiply by the brackets, you get back these two terms up here. So our positive x bar need -1x. So this should probably be -1, right? -1 by 4 is -4. So this works. So we factorize again. I'll get x minus 1, x plus 4. Okay. So you say either one bracket is 0, okay? So if you multiply two brackets and you get 0, one of them better be 0, okay? At least one of them is 0. Because both brackets have a solution for x, they can't both be 0 at the same time, because it means x will have two values at the same time, which is madness, okay? Do this again. Either x equals 1 or x equals -4, okay? From the equation, we see that the curve cuts the y-axis at y equals -4, right? Because that's the constant term. The constant term in a quadratic is the point where it cuts the y-axis as your y-intercept. So y equals ax squared plus bx plus c. The constant term is the c where it cuts the y-axis. So it cuts the y-axis at 4. 4 is the constant in the expression. But it's not so important. That's just, by the way. The more important thing is the x coordinate. So we don't really need this. But just reviewing the theory for you, right? So it's not needed in question, but I just put it in there so just to revise. So how does this curve looks like? It looks like an upside down U that cuts the x-axis at 1 and -4. Right, so let's probably draw that as a diagram. So here, look at this diagram. You see, when x is -4 and when x is 1, it cuts the x-axis. At a value by value of 4, it cuts the y-axis, but we don't care about that. We're really interested in the area enclosed by the axis on the curve, which is this triangular area to the right here. So we need to integrate the function, this function here, between 0 and 1. Right? So the area curve so this could have meant two areas. It could mean a big area here or the smaller area here. So I could just rephrase this. So they want the positive x-axis area and the y-axis, right? Positive x-axis, y-axis, the curve, right? So three things. So if you look here, the positive x-axis is this right-hand side x-axis. The y-axis is this part here, and the curve is this downwards part here. So is this area on the right, the smaller area between the curve and the axis? There's a bigger area between the curve and the axis here. They want the smaller area, okay? The difference doesn't matter, it's equally difficult to find both because you have to integrate between two limits. So you have to find an integral like this here. So let's do that. What is the original question? Is it here? So so this is a curve here, 4 minus 3x minus x squared. I'm integrating between 0 and 1. So the lower limit is 0, and the upper limit is 1. So this is the original function. Remember, you're given a gradient function, which is 4 minus 3x minus x squared. We need to integrate that now between 0 and 1. So let's go about doing that. So what is the integral of 4? With respect to x is 4x, right? What is the integral of 3x? This, you take the x power, which is 1, you add 1 to it, you get 2 and divide by that. So this is a fraction. So we call it 3x over 2. And then x squared, we integrate x squared, you increment the 2 by 1, you get 3 and you divide by 3. So again, this is a fraction. Okay? So you integrate each one 1 by 1 and you leave the sign. Integral of 4 is 4x, integral of 3x is 3x squared. 3x squared over 2. And integral of x squared is x cubed over 3. Now we're ready to substitute. So wherever you see X, you put 1 and then you subtract that from wherever you see X, you put 0. So this here will be 1. This 3x squared will be 1. This x cubed will be 1. Um, okay. And then you take out these limits here. You don't leave them in. So you integrate the function, the gradient function, to get the original function. You substitute 1 that is over here, and you substitute 0 is over here, and subtract it. So this is 4 minus 3 over 2 minus a third. This 3 over 2, this is just a third, and then all this here turns out to be 0. This question is easy. The evaluation part is easy in a sense. Right? The left bracket, 4 minus 3 over 2 minus a third. It's really just fractions where I need to take out this 0, 1 here. I need to take out this 0, 1. 4 is really a fraction. So you can write everything as 6. So you multiply so you multiply this by 6 above and below. You get 4 6 are 24 over 6. You multiply this by above and below by 3. So 3 over 2 is 9. 9 over 6. And you multiply above and below by 2 here. A third is 2 over 6. So I did, I just convert everything to 6. And then now I could just add these numbers together. So 24 minus 9 is what? 15? 15 minus 2 is 13. So you're 13/6 units. And we always say unit squared because it's a measure area. And area is always something squared. Like if you give an area, say area is 5 meters squared or millimeters squared or inches squared, square inch, right? Area is a squared quantity because it's area by area, right? So this here, this is the value, there's the answer here for this. This is how you do a question like that. It's not a lot of complicated mathematics. It's solving a quadratic, sketching a curve, and then substituting to find the integration formula, like integrate 4 to integrate 3x to integrate x squared and so on. And you just substitute and subtract and you get these things together. So I hope you'll understand that. Now it could get a lot harder, right? With finding areas. So you see, this example talks about the area between two curves. So you have to sketch a curve to know which curve comes on top because that is the top area and the curve that comes underneath, that's the bottom area. When you subtract them, you'll get a positive area, okay? The area under the curve F2 here is a lot bigger than the area under F1. So it's really F2 minus F1. I have a typo here, F2 minus F1, right? Sometimes you have to know where the two curves intersect. So they give you a curve. If you two quadratics here, and you have to find out where they intersect, right? So x squared plus 1, that's a quadratic, a U-shaped quadratic at the origin, symmetrical about the y-axis. And this is a straight line. Where do they intersect? How do you know where they intersect? Because as the simultaneous equations come in, you have a pair of simultaneous equations to solve. And then you integrate between the limits. However, you have to make sure the bigger function, the function on top is the one you integrate first. Otherwise, you get a negative area, right? This shows two not so easy curves, right? To calculate the area between. Just figure out which is the area above, which is the curve above and which is the curve below, and you subtract them and then find the definite integral between the limits, the lower and the upper limit. And it's usually not a long question, you know, but it's challenging because you may have to solve an equation. Because like, where do these two curves intersect? How do you know where these two curves intersect? You gotta solve a pair of some equations each time. And the solutions may not always be easy, right? That's the area under the curve possibility with integration. Finding an indefinite integral is the first one, and finding a definite integral is the second one. It turns out the area under a curve is the positive value of this definite integral here between the limits. You have to know where the limits are. And sometimes that involves doing quite a bit of mathematics to solve that equation, right? So that's the first example here being area. They have other things like mean and root mean square values. At this level, if I ask you to find out, you know, you're expected to just look up the definition, what the RMS value is, and it's a definite integral. You just have to take your time, okay? Root mean square values, if I ask you for the RMS value, this is the function. All these things are definite integral. They're just fancy names for different constructs in reality. Like a root mean square value is the square root of the mean value of all the values. So you have mean or average value. These are different ways, different formulas to find a quantity, but they all involve finding a definite integral. I evaluate an integral after integrated with limits. That's all that is. There's nothing really fancy at all here. Same thing with volume. A volume of revolution is rotation around one of the axes. So once you rotate around the axis, you just multiply by pi x squared, as the case may be, depending on what the curve looks like and which axis you're rotating about. Okay. So you see here I have a curve f of x curving from lower x values to higher x values. If I rotate this around the x-axis, I will get this horn shape kind of thing. Integration allows you to find what that is using the formula. You see it's a definite integral again, integral between limits a and b. What you want to integrate is pi y squared dx. That's around the y-axis, sorry, the x-axis when you rotate it around the x-axis. If you rotate it around the y-axis, is pi x squared dy. So integrate with respect to y. So look at this problem here. Cellular revolution form the curve y equals 2. The curve y equals 2 is always a straight line, which this is here. If they rotate around the x-axis, is pi x squared dx. Sorry, pi y squared dx. That's what it did here. Pi y squared dx. So substitute for y squared. Y is 2, so y squared is 2 to the 4. So the integral of 4 pi dx. So you just substitute the limits and you get that. Look at this curve here. 360 degrees along the x-axis. So that is y squared dx. See here? There is a definite integral y squared dx, where multiply by pi, right? You just use your rules for what y squared is, multiply it out and solve. It's just finding another integral. Okay. You see they have the back notation that I'm using here. And some of these questions, they only get hard. Okay. But through all of this, what you have to do is evaluate a definite integral. You have to evaluate a definite integral. Depending on your application, the integral is going to look different and you're going to interpret results differently. The general volume is the integral x or y squared dy or dx. Right? They give you the formulas here. So y squared dx for rotation on the x-axis and x squared dy for rotation around the y-axis. That's really what that is. We don't need to do centroids and thing yet, but even if I give it to you, it's really just finding a definite integral. So it's just different theory, okay? But once you know how to evaluate a definite integral, you could be able to do all these topics here. Watch this. This is just standard integration. So have quartic, simplify it. More areas on the curve, more areas between curves when you look at it. So, okay, there's some notes here. If you have a curve here, f of x, between the x coordinates a and b, these are x values, then if capital F of x is the original function, meaning you integrate the f of x with respect to x. If that function is capital F of x, then the area under the curve between a and b is the definite integral of f of x dx, which is basically the integrated function that you get, substitute a and subtract it from the substitution of b. So we saw it here in this example. This is the curve, and they wanted the area between the positive x-axis, y-axis, and the curve, right? We drew a diagram of the curve here, and they wanted this shaded area here, right? that is between 0 and 1. So we integrated between 0 and 1. And when we integrate the function, we get this new function here in square brackets. This notation where the square brackets has a upper and a lower limit, it means to substitute it into the square brackets. So we substitute the upper limit, and then we subtract that from the substitution of the lower limit. Okay. For volumes of revolution, you could rotate around the x-axis or the y-axis. Now, you can find there is an area under the curve between the curve and the y-axis instead of the x-axis, but we don't typically do that, but it's just integrate with respect to y. But the function would have to be different, right? So here now, volumes of revolution. If you rotate it about the x-axis, you get a solid object. Is pi y squared dx, and integrate between the ordinates a and b. If you have y ordinates a and b, then you integrate an x squared with respect to y. And if it's x squared, you have to change the subject of the formula, the original function, to integrate with respect to y. So for this question here, we'll just do it's difficult to do about the y-axis, right? So if you rotate this, the same question we had before, you rotate the positive area 360 degrees around the x-axis, find that volume. Okay, that's the volume we want you to find, which is this shaded area here, rotated around the x-axis. So, I mean, you could just plug it into the formula and find the integral. Okay, that's really what they're doing here. Like if they give you a question here, say, we'll look at this one here, x squared plus 2, right? So it's y squared dx, pi y squared dx. So they put pi, and then they substitute for y. Y is x squared plus 2, so it's all that squared and integrate with respect to x. You could put out, you could expand this out, pull out the pi on the outside, integrate, and then apply the limits, okay? Usually this question over in 5 or 6 lines. You leave your answer in terms of pi, right? Or as, you know, as a fractions, like 2 pi over 7 or something like a unit square. For volume, it will be cubic units, so you say units cube, okay? These questions are not very long, and the amount of algebra you have to do is kind of minimal. It's usually substitution after you integrate. There's not a lot of algebraic gymnastics. So try this question here and tell me what answer you get. So there's the same question as before. We found a shaded region. Is that region in blue there, positive x-axis, the y-axis on the curve, right? So you want to rotate that one complete revolution around the x-axis. So rotation around the x-axis is given by, you know, the formula up here, integral pi y squared dx. So pi y squared dx between the lower and the upper limit. The lower limit is 0, the upper limit is 1. So 0, 1 pi by this thing all squared. Remember, whatever y is all squared because it's y squared. Y turns out to be this quadratic here. Square means you multiply it by 2 brackets. You take out the pi, since it's a constant, you pull it out to the integral side. And we take our time and we multiply it, right? So everything in this brackets on the left multiply by one each term inside here. So these 3 terms multiply by 4. What we'll get? 4 4s are 16, minus 3 by 4, minus 12x, minus 4x squared. Then we multiply everything here by negative 3x. 4 by negative 3x minus 12x, negative 3x, positive 9x squared, negative x squared, negative 3y, positive 3x cubed. Everything in here by negative x squared, that's 4x cubed, sorry, 4x squared negative, positive 3x cubed, and positive x4, right? And then we want to collect like terms together to simplify this, right? So rewrite this over here. So let's put the x4 together, right? So put the x4 in front here. Then I have x cubed terms. So how much x cubed terms I have? I have all these. I have 3x cubed plus 3x cubed. That's 9x cubed. Right? So I could take out this 3x cubed here, this 3x cubed here. What am I left with? I have x squared terms. So I have 9 minus 4 minus 4. That's 9 minus 8, which is just x squared. Right? So the 49, take out this 4. And the x terms, minus 12 minus 12 is minus 24. And then you will just have the 16. Right? Positive 16. So it's really just to integrate these things here now after you simplify. So put limit 0, 1, and you're gonna get a lot of fractions here now. X4 is x5 x5 over 5, right? I might have to go big on this. Right? So if you integrate x5, you get x5 over 5. This is 9x4 over 4. Integral of x squared is x cubed over 3. Oh yeah, this 9 should be 6. For some reason I add 3 and 3 and I get 9. So it should be 6 there. So this is 6 over 4. Believe it as 6 over 4, reduce it after, right? Of the of the 24. 25x squared over 2. I'll reduce after, right? You increase the power of this x by 2 and then you divide by 2. So 24x squared over 2. Notice the signs remain, right? And the 16, the integral of 16 is just 16x, right? So the 6 over 4 is a 3 over 2. The 24 over 2 is 24 is 12, right? So we take this out. Uh, the wrong one I take out. This is 6 over 4. Let's change the new one. Right, so this look a little better here. And then you just because it's between 1 and 0, we substitute 1 and we substitute 0 and we subtract it. All right, so take out the 1 and 0, and it's these two things. Right. Now the second thing will be 0. Right? The second thing will be 0. Wherever we see x here, we want 1. Wherever we see x here, we want this here. Right? So let's write that in. Everything there is 0, basically. And everything here is 1. It's really just arithmetic at this point, adding fractions. Right? So it's essentially all of this here. Right? So this entire thing here is 0. So I'll end up with this is 1/5. It's 3 over 2. This is 1/3. Minus 12 plus 16. Right? So the 5, 2, and 3. Wow, this is some fractions. Minus 12 plus 16. This is 4. So we know it's 4 plus these guys, right? Now 2, 3, and 5 are all prime numbers. So you have to multiply them to find the answer. So it's stuff over 30. Right? That could represent everything over 30. So 5 2s are 10, 10 3s are 30. So all of these guys here is something over 30. So I think this should be it. So 5 2s are 10, 10 3s are 30, 30 by 4 is 120. 6 by 5 is 30, so up here be 6. 15 by 2 is 30, so 15 by 3 is 45. 10 by 3 is 30, 10 by 1 is 10. So you just how to add up all of this now. So this is 45 and 10 is 55, 55, 65, 75, 175 plus 6. Now, all of these things had a pi, had a pi in front here that we forget. So you had to you'll forget that pi, right? As always, have to know that your answer has the pi inside it. When multiply by pi, as they really asked, right? Oops. Take out these brackets now. So it's 181 pi over 30 units cubed. Now, I mean, if you realize this here, right? Where's the complicated algebra in this question? Is really figuring out the roots here, solving this equation equals 0. After here, when you apply the rules of integration to move from the first line to the second line, all the lines after that is just substitution. So it's not really hard, but if you want to show all your work and you want to work at fractions and equivalent fractions. Similarly, this question here, look at the first two lines. First line is the formula. The second line is the expression. We had to expand this out, right? So this is some algebra here from CSEC. This is CSEC algebra, being able to expand this out. After you expand this out, you collect like terms together. When you start to integrate, you see from this line here, 1, 2, 3, 4, 5. See the fifth line? Up until the fifth line, you've been doing CSEC maths. To go from the fifth line to the sixth line, you apply the integration formula, right? But after the sixth line, it's just substitution, It's just substitution and simplification and algebra and that kind of thing, equivalent fractions. All is the CSEC math. This entire question here, the only thing that is not on CSEC is from line 5 to line 6. Right? The coordinate geometry, all these things that is using from your CSEC, from your form 5 days, right? Where a line intersect a curve or the shape of a quadratic and stuff like that. Is calculus is built on top of the maths you already know. It's just one or two small little theorems or results, but after that, everything else is the stuff that you know already, right? All right, so I hope you all understood that long set of working. In the textbook, you would see there are some questions here. Find the area under a curve between ordinates. And if it rotated around the x-axis, find the volume. Those are very typical integration type problems. You see it finishes in like 3 or 4 lines. Once you integrate and substitute, yeah, it finishes pretty quickly, right? So you really just have to know these formulas here. These two formulas here is for volume, and for area is the definite integral. But you see, it gets more complicated when curves intersect with lines on other curves, right? Centroids of shapes, we could talk about this, but it's really just a formula. Okay, it's still integration, it's just a formula. So if they ask you, oh, find a centroid of a shape between blah and blah, you know, you just, okay, what are the limits? C and D, whatever, yeah, just apply the two integrations and then divide, because it's two coordinates you're dealing with. Right? I would leave this exercise up for you to read and understand it, but it's still integration. You still have to integrate at some point, right? So you have centroid and area between the curve and the x-axis, and then centroid in the y-axis. What is centroid is that point on a shape where the center of gravity appears to act, right? Where the center of mass, right? These are more mechanical engineering type problems here, where you do the summation in both directions. So it's really two integrals you have. They're not very difficult, but it's almost as hard as finding the area under a curve or the volume and revolution. It's just formulas to apply, right? I may not do this, I may not give you questions on central and area. Area under the curve and volume and revolution, we'll stick to that. Theorem of Papas, these things are a little more advanced, right? We don't really talk about that in this course. But this is certainly applications in your other courses in construction. Eh? Don't be surprised if you're doing a construction course and the guy asks you all to find the center of mass or the centroid area of a shape. And you're there like, what? How you just do that? Well, he said, well, you all know integration, right? So it's just a formula. There's two coordinates you have to find, the average x and the average y, and they essentially a ratio of two integrals. One is the xy and one is the y or x. Yeah. But I am not going to bring this, nor am I bringing theorems of Papas on your assignment. The assignment is straightforward area or volume they will ask you to find, nothing too complicated. But these things are in this maths book because it will come in your other construction engineering courses, right? Neither am I bringing this. In fact, when I give you the chapters to study for integration, let's see what I gave you here, integral calculus. 55, 56, 57, 58. Yeah, so you didn't bother with chapter 9. I didn't even give you chapter 59, right? And that's it for your integration applications there from your textbook. What I would suggest you do is do the problems, right? A good chapter to do problems in is this chapter here, the 56 and 57, right? I wouldn't bring anything like root mean square values either, but it's still standard integration. So I may not bring chapter 56, right? It will be really 55, 57, 5 and 57. And you see here is a lot of substitution. Look at this question here, the shaded area, right? Once you figure out what the integral for the shaded area is, you just integrate and you get this. You see this expression here? This is after you integrate. So from step 3 here, line 3 to line 4, all I did was integrate. Everything after the substitution. Okay? So up until this point, you're really simplifying using your algebra. And after the integration, you're just simplifying using algebra. So the bulk of our integration question is really a CSEC maths. Factorizing, completing the square, equivalent fraction, substitution, changing subject of the formula, difference of two squares, roots are quadratic, minimum, maximum value, curve sketching, completing the square, quadratic formula, partial factorization. That's all them things is what I was doing with you all this time. You see here from lecture 1 to lecture 9, that's what I've been doing up until this point, SIDS and everything, is to get your basic algebra skills up to a certain point, so that when you have to do these more advanced topics now, all these topics that you did before is actually part of a question. An integration question have 4 or 5 topics from maths that will come at you. Same thing with a differentiation question where you had to solve. Yeah, remember we had to solve equations to find stationary point. You had to solve a polynomial equation. That's roots of equation, quadratics, and you know, completing the square and finding roots and the quadratic formula and these things, right? All of those things are baked into these topics, these more advanced topics. A differentiation question and I have 4 or 5 topics on C-second side of it. So I hope this makes sense what the integration is. Integration really is you're given a gradient function f of x and you want to find capital F of x, which is the original function. When you don't have limits, you're just integrating here. That's called an indefinite integral. When you have ordinates, or as we call limits, you just substitute into the final expression. Is the upper ordinate substituted minus the lower ordinate substituted. That's the value of the definite integral. It turns out that the area under a curve is a definite integral. Similarly, the volume around, when you rotate it around the x-axis between two x ordinates, it's the value of a definite integral, okay? I'll probably just give you a question here for homework for you guys to try. So we have a question here. A region R is enclosed by the curve on a line, right? So x plus y is 5 and the curve y is 4 over x. Find the area of the region R and the volume of the solid formed by rotating R through 360 degrees. This curve is called a hyperbola, okay, in the inverse function. We could look at it. Let's see if we could look at it. We'll try looking at it in Desmos, right? Let's see. Let's see how it looks like. So y equals 4 over x, right? Y equals 4 over x. That's 4 over x. And the line x plus y equals 5. So this is how anything over x, this is how it looks like, right? I can make it bigger so you can see. Like the curve 1 over x, again, it's more, it's sharper, closer, the curve's closer to the origin, right? There's 2 branches, as you see here, it's 2 branches. There's the inverse function. It's something you should have experienced before in life, right? Y is inversely proportional to x. So as x gets bigger, 1 over a very big number, y gets smaller. Y is 1 over that, right? Similarly, as x gets very, very close to 1, it is a fraction, right? 1 over a very small fraction is a very big number. So y gets bigger. So you have this symmetrical curve here. Well, the symmetrical curve you have here. If you increase the top, like you say 10, it moves away. The bigger the numerator, it moves away from the origin. See, we have more space here. So 4 over x looks something like that. Now, what is a straight line? A straight line, y equals mx plus c. So I could say x plus y equal 5. If I write that here, x plus y equal 5. See? A straight line will only be in one part of the xy plane. It doesn't duplicate like both sides here. You follow? So that this is the region here enclosed by the two curves, right? Forget about this other branch of the hyperbola on the left bottom here. We're really interested in this top part here. That's the shaded region is that region there, right? That's the region enclosed by the curve. So I could probably say, I could say 4x right? Right, so that's this region here, right, between the curves, right? And you ought to figure out where those points intersect, right? That shaded region is what I'm trying to find. That's R. That's what R is. R is that shaded region, right? You want to find the area of it, and you want to find the volume when it rotated through the x-axis by 360 degrees. So now we're using this formula here for rotation on the x-axis. Rotation around the x-axis. Now makes this, underline this here. This is supposed to be y-axis. I made a mistake here. Rotation about the y-axis, right? Y-axis, the formula is different, and these are y coordinates here, right? So essentially, this formula you're using, and we need to. You will have to figure out what the coordinates are, where they intersect, and then is the area of the big curve over the small curve. Let me see it here. You see an area between curves? Look, area between two curves here. So the top curve, which is F2, minus the area of the bottom curve, which is F1, right? Between the same coordinates A and B. If you do that definite integral, those two definite integrals, and you subtract it, you will get the answer. And I have an example here. Find, determine here, this page 485, problem 11. Find the area enclosed between a curve and this straight line. They found where the two curves intersect, right? And they know, okay, minus 3 and 2. So that's the integral. The integral goes from minus 3 to 2. The top curve, which is the straight line, has a bigger area, minus the bottom curve, which is the curve underneath, which has a smaller area, right? Top minus bottom. I just do the integration, substitution, and finish. Leave your answers like how I had it here with square units, right? When I give an answer, I say units cube, and leave pi in it if you have a one. Go and multiply that out here, right? So, I mean, you could use tools like Desmos to help you, but I mean, in an exam or in an assignment, you can't give me Desmos as an answer. You can't go and plot this and give me an answer, or plot it on a graph and calculate. That's not answer, that's art. I'll give you 0 marks for that. I want to see the mathematics, how you know where the curves intersect with the line. You see how I did it here? Where you know where it cuts the x-axis. I have to solve the equation. A sketch is really just to help you, right? But we did a sketch before where I didn't need to plot a graph or anything like that. It's a quadratic, you should be able to sketch it on your own, right? So that's the region there, and we want to know the volume of that. Leave your answers in exact form, improper fractions, not mixed numbers, right? Leave all the answers as improper fractions with surds or whatever in exact form in terms of pi where necessary, right? So good luck with this question. This is a nice, fairly simple to intermediate question. This is not a hard question. Yeah. You all never really see a hard question from me.